Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 13 of week 3. We are talking about performance characteristics of instruments and data analysis part 2. Today, we will talk about an important aspect of error analysis. Imagine measurement of by any particular instrument. Any instrument consists of several components. Now, there may be inaccuracy associated with each of these components. So, the inaccuracy of each component will contribute towards computation of total inaccuracy. So, today we will learn if the individual component inaccuracies are known, how to combine them to get overall inaccuracy for a measurement. The reverse problem is even more interesting. Suppose I want to measure a particular quantity with a given inaccuracy or accuracy, whatever you say. So, what will be the permissible inaccuracy for individual component? So, today's topic is combination of component errors in overall system accuracy calculations. This is also known as propagation of uncertainties in compound quantities. After describing the theory part of it, we will take a numerical example to clarify the concept in more details. A measurement system is often made up of a chain of components, each of which has individual inaccuracy. We may also use measurements from various instruments to compute some quantity. Each instrument may be associated with some inaccuracy. For example, Reynolds number is given as dV rho by mu. Imagine a liquid flows through a pipe of diameter d, the velocity of the liquid is v, the density of the liquid is rho and the viscosity of the liquid is mu. Then the Reynolds number is computed as dV rho divided by mu. Now, you can use various instruments to measure diameter of the pipe, velocity of the flow, density and viscosity of the liquid. Then compute Reynolds number as dV rho by mu. Now, each of these measurements are associated with some error. So, how do you combine these errors to compute the overall error in the computation of Reynolds number? So, if the individual inaccuracies are known, how do you compute the overall inaccuracy? The reverse problem can be specified as follows. If we specify a certain accuracy in a computed result, what errors are allowable in the individual measurements or instruments? Let us say I say the Reynolds number has to be measured with 99% accuracy. So, what are the maximum inaccuracy allowable for measurement of diameter, velocity, density and viscosity? So, this is known as reverse problem. The previous problem was forward problem, where the individual component inaccuracies are known, we combine them to get the overall accuracy or overall error. In the reverse problem, we specify that a certain accuracy in a computed result is required, then ask what errors are allowable in the individual measurement. So, let us consider that y, a quantity that I am computing or measuring, is a function of various other measurements. So, y is a function of x 1, x 2, x 3 up to x n. For small changes in independent variables x I, a Taylor series expansion gives an approximation of change in dependent variable y. So, what we mean is, if these independent variables x 1, x 2, x 3 etcetera changes by small quantity, a Taylor series expansion will allow me to get an approximate change in the dependent variable y, which can be computed as this. So, the change in the dependent variable y can be computed as del f del x 1 into delta x 1 plus delta f del x 2 into del x 2 and so on and so forth. In other words, it is a sum of quantity like del f del x I delta x I, which is delta y. Now, we consider this del f del x I as sensitivities of y to changes in particular x, because del f del x I represents the changes in f with respect to change in x I. Change in f is nothing but change in y. So, del f del x I are sensitivities of y to changes in particular x, and delta x I and the delta x I can be considered as uncertainty in x I. So, delta x, which is this, these delta x represent uncertainty u x I in each measured value. So, delta x 1 is uncertainty in measurement of x 1, delta x 2 is uncertainty in measurement of x 2, and so on and so forth. Then the corresponding uncertainty in y, which you can represent as u y, can be computed as del f del x 1 plus u x 1 plus del f del x 2 u x 2 plus del f del x 3 u x 3, so on and so forth. Such terms has to be added up to del f del x n u x n. So, the maximum value of uncertainty in y, that is u y max, will be obtained when all the uncertainties have the same sign. If different uncertainties have different signs, then some of them will be cancelled, some of them will cancel each other out. So, the maximum value of uncertainty will be obtained when all the uncertainties have the same sign. Please note that this will be the worst possible case. So, to get the maximum value of uncertainty, what can be done is, you can add the absolute values of the term del f del x 1 u x 1, del f del x 2 u x 2, and so on and so forth. But the probability of such occurrence is small, because it is unlikely that all the uncertainties will have the same sign. Some uncertainties will be positive, some uncertainties will be negative. So, the probability of occurrence of all uncertainties having the same sign is small. The more realistic value of uncertainty will be to compute the root sum square value. This gives equal weights to positive as well as negative values of uncertainties. So, to get the most probable uncertainty, instead of adding del f del xi uxi terms, absolute values of such terms, we should compute root sum square value. So, this is how we do the root sum square values. So, first we square both the sides. So, I neglect all the cross terms and square both the sides to obtain this equation. So, from this the most realistic uncertainty u y can be obtained as square of these quantities, which is this. So, this can be written in a compact form as overall estimated uncertainty due to combined effect as this. So, basically you are writing the same equation in more compact form. So, we started with y is a function of x 1 up to x n, then said using Taylor series expansion we can compute change in y due to change in x 1, x 2, so on and so forth as sigma delta f I delta f delta x I into del x I. Then we considered del f del x I as sensitivity and delta x I as individual uncertainty. So, this sum gave the overall uncertainty in y. So, to get root sum square error, we squared both sides and got this after neglecting the cross terms. Then u y is obtained as square root of this term, which is this. So, this is written in more compact form as this. So, note that this is the cross terms that I was talking about, we have neglected. So, these terms will be here, which we have neglected. Uncertainty can also be expressed as percentage. As we saw in previous slides, the overall estimated uncertainty due to combined effect is this. Now, we can also express this uncertainty y as percentage as follows. So, u y divided by y multiplied by 100. Now, let us look at the reverse problem. We expect that final results must meet some specified accuracy. What is the accuracy needed for each instrument or measurement? So, this is again the most probable uncertainty which obtained from root sum square error. Now, in this expression, in case of forward problem, u x I were known. So, if the functional form of f is known, you can compute the sensitivities by taking the derivatives del f del xi and then just use this relation to compute the overall uncertainty in case of forward problem. In case of reverse problem, we have been given a specified value of u y. So, I am asking what are the allowable or maximum values of u x I. So, given the specified accuracy for the end result, what are the maximum allowable uncertainty in each measurement or instrument, which is represented as u x I. Note that there is no unique solution exists for such problems, because there are many combinations of individual errors which may give the same overall error. So, because there exist many combinations of individual errors which may give the same overall error or same overall accuracy, there cannot be any unique solution for this reverse problem. But we have to get some working solution. So, we make use of something called method of equal effects. So, this is a simple approximation that we will make, and it will allow us to get at least one working solution. The method of equal effects assume that each term contribute equally to the overall error. So, this was the expression we obtained for most probable error when we computed the forward problem, when we computed the error for the forward problem. Now, u y is given, these needs to be computed. But please note that several combinations of u x I can lead to the same value of u y. So, no unique solution exists. So, to get an working solution, we will make use of an approximation known as method of equal effects. Here we assume that each term, each of these u x I contribute equally to the overall error u y. That means, the del f del x 1 u x 1 is equal to del f del x 2 u x 2 up to del f del x n u x n. All these terms we consider equal. The moment we do that, it is now possible to get a working solution. So, the moment I say that these are all equal, I can write this. Let us say these are all equal to del f del x I u x I. So, you have n such terms which has been summed up. So, value of u y is simply this. From here, it is possible to compute u x I, the individual uncertainty. So, u x I is u y divided by this term, which is this. This concept can be used for various functional forms between y and x. say we are computing the combinations of computing errors, combinations of component errors in overall system accuracy calculations for a product function. So, y is given as follows: y equal to x 1 to the power a 1 into x 2 to the power a 2 up to x n to the power a n. The same methodology can be used. We first compute the partial derivatives, and finally get del y del x I. Note that y is same as f, and then we make use of the expressions to get E y by y as this. So, basically you follow the same methodology. You have a product function here, so the derivatives has to be computed accordingly. Please note that you need to know the functional form, so that you can compute the derivatives. Now, let us consider you have additive function. So, y equal to a 1 x 1 plus a 2 x 2 up to a n x n, which can also be written as sigma a I x I. Again you find partial derivatives. After finding partial derivatives, you straight away make use of this relation to get overall uncertainty as this. Now, to make the concept more clear, we will take two numerical problems. First example we consider is about the resistance of a copper wire. The resistance, which is represented as R of a copper wire, is given as R equal to R 0 into 1 plus alpha into T minus 20. You know the resistance of a wire changes with change in temperature, and that relationship is expressed here, R equal to R 0 into 1 plus alpha into T minus 20, where R 0 is 6 ohm plus minus 0.3%, and this is the resistance at 20 degree Celsius. So, R 0 is given as 6 ohm plus minus 0.3%. Note, uncertainty is in R 0 is expressed as plus minus 0.3%. The term alpha is the temperature coefficient of resistance and given as 0.004 plus minus 1%. So, the inaccuracy or the uncertainty in the measurement of alpha is given as plus minus 1%. If the temperature is measured with an accuracy of plus minus 1%, calculate the resistance of the wire at 30 degree Celsius and its uncertainty. So, I have the value of R 0 at 20 degree Celsius, uncertainty specified, value of alpha specified and uncertainty also specified. The temperature is measured with accuracy plus minus 1%. So, inaccuracy of all these individual measurements are given. I have to combine these uncertainties to get the overall uncertainty in R. So, first let us compute the nominal resistance at 30 degree Celsius. So, it is straight away make use of the equation R equal to R 0 into 1 naught plus alpha into T minus 20. So, if you use that, you get a value of 6.24. So, this is R 0, the nominal value alpha T equal to 30 degree Celsius minus 20. So, you get 6.24. Now, I have to find out the partial derivatives, those del f del xi terms. So, here x1, x2, x3 are there in the form of R0, alpha and T. So, I compute del R del R0, del R del alpha and del R del T. You have R equal to R0 into 1 plus alpha T minus 20. So, you take del R del R0. So, del R del R0 will be this part, which is 1 plus alpha T minus 20. So, put the nominal values of alpha and T equal to 30, you get del R del R0 as 1.04. Similarly, you find out del R del alpha at 60, del R del T as 0.024. And now, individual uncertainty. Uncertainty in R0 is given as plus minus 3%. So, 0.003 of 6, which is the nominal resistance. So, it was given as 6 plus minus 0.3%. So, this value is 0.018 ohm. Similarly, alpha, uncertainty in alpha was expressed as 0.004 plus minus 0.1%. So, you compute this value as this. Measurement of temperature is given as plus minus 1%, plus minus 1 degree Celsius. So, all these uncertainties are known, and now you have to make use of this equation to compute the overall uncertainty. So, simply put all the values for R0 term, alpha term and T term. So, the overall uncertainty is 0.0305 ohm. We can also express it as percentage uncertainty. So, percentage uncertainty is given as UR divided by R into 100. This R is that nominal resistance. So, if I compute this, it becomes 49%. So, let us quickly take another example. Two resistors R1 and R2 are connected in series. The voltage drops across each resistor are measured as E1 equal to 10 volt plus minus 0.1 volt and E2 equal to 1.2 volt plus minus 0.005 volt. Also, the resistance R2 is measured as R2 equal to 0.0066 ohm plus minus 0.25%. Determine the power dissipated in resistor R1 and its uncertainty. So, two resistors are connected in series as shown in the figure. The voltage drop across each resistors are measured and individual is also known and the uncertainty in it is also specified. We have to determine the power dissipated in the resistor R1 and its uncertainty. So, power dissipated is power equal to voltage into current. Current through both the resistors is same. So, the current I can be computed as E2 by R2. So, then power is E1 into I, which is E1 E2 by R2. The nominal value of power is straight away can be obtained from this equation. So, I put all the values given and get as 1818.2 watt. Uncertainties in E1 and E2 are given as 0.1 and 0.005. Uncertainty in R2 is also given 0.25% or 0.0066, so which can be computed as 1.65 into 10 to the power minus 5. So, now from the relationship of power, I have to compute the partial derivatives which corresponds to sensitivities. So, we compute del P1 del E1, del P1 del E2 and del P1 del R2. So, the values are obtained as this, and now I combine the terms like delta P1 del E1 into uncertainty in E1 plus delta P1 into del E2 in uncertainty E2, such terms using the most probable root sum square error, and I get the value as 19.16 watt. I can also express this in terms of percentage. So, uncertainty in P1 divided by P1, the nominal value, into 100 is the uncertainty expressed as percentage. So, this is computed as 1.05%. So, we considered two problems after introducing the concept of error analysis or propagation of error. We consider two cases. If the individual component errors are known, how to compute the overall error as a forward problem, and as a reverse problem we consider if individual uncertainties are known, if the final accuracy or the final tolerable error in the final result is known, what are the maximum allowable uncertainty in individual components or individual measurements. We considered two numerical problems which will help you to understand the concepts better. So, we will close our lecture 13.